because it's a very different way of writing code. Normally you write code and you can kind of think it through and understand.
Yep.
Whereas a neural network, it's this, you write an equation, a complicated equation inside a loop, and then you run the loop. And now good luck figuring out what it does precisely. And that connects to neural nets not being interpretable. But you could also argue that the difficulty of understanding what neural networks do is not a bug, but it's a feature. Like, we want to build intelligence. Intelligence is not simple to understand. We can't explain how we do the cognitive functions that we do, how we see, how we hear, how we understand language. So therefore, if computers can produce objects that are similarly difficult to understand, not impossible, but similarly difficult, it means we're on the right track. And so all those things helped me converge on neural networks fairly early on.
Yeah. What year was it when you sort of like remember initially getting excited about neural networks and being pretty convicted?
Like early 2000s. I started working with Jeff Hinton in 2003.
Yeah.
So quite a while ago now.
Long before, I mean, obviously the craze kind of started around 2010, and so
that's right.
There was a good, like, I think this is a common theme whenever you look at sort of anybody who works like in any sort of field that becomes very big. But there's a long stretch of like, you know, wandering in the desert, maybe is one way to put it.
Yeah, I mean, definitely lots of perseverance is required because you don't know how long you're going to stay in the desert. You just gotta endure.
Yeah.
And that's very helpful.
And did you expect, like, I mean, obviously today neural networks do some pretty incredible things. Like, did you expect back in 2003 or early 2000s that, like, in your lifetime you would see sort of the things that we're seeing now with AI and machine learning?
I was hoping, but I did not expect it. Back then, the field of AI was on the wrong track. It was in a mindset of rejection of neural networks.
Right.
And the reason for that is that neural networks are difficult to reason about mathematically, while other stuff you can prove theorems about. And there is something very seductive and dangerous about proving theorems about things.
Yep.
Because it's a way to showcase your skill, but it's not necessarily aligned with what makes the most progress in the field. But I think that neural networks are as successful as they are precisely because they're difficult to reason about mathematically. And so anyway, my earlier hope was to simply to convince the field that they should work on neural networks rather than the other stuff that they were doing.
Yeah.
But then when computers started to get fast, then my level of excitement and about their potential has increased as well.
Yeah. And so what are your aspirations today? Like, what is the, like, in your lifetime, what's the thing I mean, I think it's obvious from the OpenAI mission set, but.
Yeah, I mean, exactly right. So now the hopes are much larger. Now I think we can really try to build not only really powerful and useful AI, but actually AGI, make it useful, make it beneficial, use it to solve, and make it so that it will be used to solve a large number of problems and create lots of amazing applications. That's what I'd like, that's what I hope to see happen.
Yep. And then, you know, obviously along the way, you had been doing a lot of this research and doing a lot of groundbreaking work at Google, and then you sort of left and started OpenAI with Sam Altman and Greg Brockman and a bunch of others. What were your kind of goals with starting OpenAI at the outset? What was sort of like the initial conception and the initial vision, and what did you hope to accomplish by starting sort of a new lab?
There were multiple motivations on my end for starting OpenAI. So the first motivation was that I felt that the way to make the most progress in AI was by merging science and engineering into a single whole, into a unit, to make it so that there is no distinction, or as little distinction as possible between science and engineering, so that all the science is infused with engineering discipline and careful execution, and all the engineering is infused with the scientific ideas. And the reason for that is because the field is becoming mature, and so it is hard to just do small-scale tinkering without having a lot of engineering skill and effort to really make something work. So that was one motivation. I really wanted to have a company that will be operating on this principle. Another motivation was that I came to see AI technology in a more sober way. I used to think that AI will just be this endless good, and now I see it in a more complex way, where I think there will be a lot of truly incredible, inconceivable applications that will improve our lives in dramatic ways.
Right.
But I also think that there will be challenges. I think that there will be lots of problems that will be posed by the misapplication of AI and by its peculiar properties that may be difficult for people to understand. And I wanted a company that will be operating with this awareness in mind, and it will be trying to address those challenges by, as best as possible, by not only working on advancing the technology, but also working on making it safe, and also working on the policy side of things, as much as is rational and reasonable, to make the whole be as useful and as beneficial as possible.
Totally. And I think it's something we agree on. I mean, I think one thing that is very obvious to me is that AI is something that's going to, which countries have access to AI technology and the ways in which they use them are going to define how the world plays out over the course of the next few decades. Like it's just, I think that's how, that's the path we're on as a world.
That's right, among many other things.
Right, right. And I think this thing that you mentioned around sort of bringing together the science and engineering, I think it's quite profound. I think for a few reasons, right? Because like one is that, first of all, I think a lot of the best, the most incredible, innovative things happen oftentimes from sort of blurring the lines between disciplines. Like Apple is one of the best examples where from the very beginning, they were always like, hey, we're blending hardware and software, and that's our special sauce. And obviously it's produced some incredible things. And I think a lot of other research labs, they operate in a very sort of scientists tell the engineers what to do mindset, which is counterproductive because you really need to understand both very well to understand what kind of the limits of the technology are.
Yeah, that's right. And on that point, you may even say, isn't it obvious that the science and the engineering should be together? And on some level it is, but it just so happens that historically it hasn't been this way. There's a certain kind of taste, like empirically, it has been the case in the past, less so now, that people who'd gravitate to research would have a certain taste that would also make them less drawn to engineering, and vice versa. And I think now, because people are also seeing this reality on the ground, that to do any kind of good science, you need the good engineering, then you have more and more people who are strong on both of these axes.
Totally. Yeah, and I think that, switching gears a little bit to kind of the GPT models, like this is a great illustration, right? Because the GPT models are impossible without incredible engineering, like the sort of, but yet they still require novel research, they still require novel science to be able to accomplish. And they've obviously been some of the biggest breakthroughs in the field of AI as of late, and sort of blown open many people's imaginations about what AI can accomplish, or at least increase people's confidence that AI can accomplish incredible things. I'm kind of curious about, originally when at OpenAI, when you've been working on these language models for some time, what were the original sort of research inspirations behind it, and what were the original sort of things that led you all to say, hey, this is something that's worth working on, worth scaling up, worth continuing to double down on?
So there have been multiple lines of thinking that led us to convergent language models. There has been an idea that we believed in relatively early on, that you can somehow link understanding to prediction, and specifically to prediction of whatever data you give to the model. Where the idea is, well, let's work out an example. So before diving into the example, I'll start with the conclusion first. The conclusion is that if you can make really good guesses as to what's going to come next, you can't make it perfectly, it's impossible. But if you can make a really good guess, you need to have a meaningful degree of understanding. In the example of a book, suppose that you read a book and it's a mystery novel, and in the last chapter, all the pieces are coming together, and there is a critical sentence, and you read the first word and the second word. Now you say, okay, the identity of some person is going to be relieved, and your mind is honing in on like, it's either this person or that person. You don't know which one it is. Now, maybe someone who read the book and thought about it very carefully says, I think it's probably this person. Maybe that, but probably this. So this example goes to show that really good prediction is connected to understanding. And this kind of thinking has led us to experiment with all kinds of approaches of, hey, can we predict things really well? Can we predict the next word? Can we predict the next pixel and study their properties? And through this line of work, we were able to get to, we did some work before the GPTs, before the transformers were invented, and with something that we call the sentiment neuron, which is a neural net which was trying to predict the next word, the next character in reviews of Amazon products. And it was a small neural net because it was maybe 4 years ago, but it did prove the principle that if you predict the next character well enough, you will eventually start to discover the semantic properties of the text. And then with the GPTs, we took it further. We said, okay, well, we have the transformer, it's a better architecture, so we have a stronger effect. And then later the realization that if you make it larger, it will be better. So let's make it larger, and it will be better.
Yeah, I mean, there's a lot of great nuggets in what you just mentioned, right? I think first is the elegance of this concept, which is like, hey, if you get really good at predicting the next whatever, get really good at prediction, that obligates you to be good at all these other things if you're really good at that. And it's I think it's probably like underrated how that required some degree of vision, because it's like early on, you try to get really good at predicting things, and you got the sentiment neuron, which is cool, but it's like that's like a blip relative to what we obviously have seen with the large language models. And so that I think is significant. And I think the other significant piece is what you just mentioned, which is kind of scaling it up, right? And I think you guys had released this paper about this kind of like a scaling laws of what you have found as you scaled up compute, data, model size, sort of in concert with one another. But I'm kind of curious, like, what's the obviously there's some intuition which is just like, hey, scaling things up is good, and you see great behaviors. What's kind of your intuition behind sort of, if you think from now over the next few years or even the next few decades, like what does scaling up mean? Why is it likely to continue resulting in great results? And what do you think the limits are, if any?
I think two statements are true at the same time. On the one hand, it does look like our models are quite large. Can we keep scaling them up even further? Can we keep finding more data for the scale up? And I want to spend a little bit of time on the data question, because I think it's not obvious at all.
Yeah.
Traditionally, because of the roots of the field of machine learning, because the field has been fundamentally academic and fundamentally concerned with discovering new methods and less with the development of very big and powerful systems, the mindset has been someone creates a fixed benchmark. So a data set of a certain shape, of certain characteristics, yep. And then different people can compare their methods on this data set. But what it does is that it forces everyone to work with a fixed data set.
Yep.
The thing that the GPTs have shown in particular is that scaling requires that you increase the compute and the data in tandem at the same time. And if you do this, then you keep getting better and better results. And in some domains, like language, there is quite a bit of data available. In other, maybe more specialized subdomains, the amount of data is a lot smaller. And that could be, for example, if you want to have an automated lawyer. So I think your big language model will know quite a bit about language, and it will be able to converse very intelligently about many topics, but it may perhaps not be as good at being a lawyer as we'd like. It will be quite formidable, but will it be good enough? So this is unknown because the amount of data there is smaller. But anytime where data is abundant, then it's possible to apply the magic deep learning formula and to produce these increasingly good and increasingly more powerful models. And then in terms of what are the limits of scaling, so I think one thing that's notable about the history of deep learning over the past 10 years is that every year people said, okay, we had a good run, but now we've hit the limits. And that happened year after year after year. And so I think that we absolutely may hit the limits at some point, but I also think that it would be unwise to bet against deep learning.
Yeah. There's a number of things I want to dig in here because they're all pretty interesting. One is this just I think this you certainly have this mental model that I think is quite good, which is kind of like, hey, Moore's law is this incredible accelerant for everything that we do, right? And the more that there's Moore's law for everything, Moore's law for different inputs that go into the machine learning lifecycle, we're just going to like push all these things to the max, and we're going to see just incredible performance. And I think this is significant because, as you mentioned about this data point, it's like, hey, if we get more efficient at compute, which is something that's happening, we get more efficient at producing data or finding data or generating data, we get more efficient. Obviously, there's more efficiency out of the algorithms. All these things are just going to keep enabling us to do like the next incredible thing and the next incredible thing and the next incredible thing. So first, I guess we've talked about this a little bit before, so I know you agree with that. But like, what do you think is where do you think, like, are there any flaws to that logic? What would you be worried about in terms of how everything will scale up over the next few years?
I mean, I think over the next few years, I don't have too much concern about continued progress. I think that we will have faster computers. We will find more data and we'll train better models. I think that is, I don't see particular risk there. I think moving forward, we will need to start being more creative about, okay, so what do you do when you don't have a lot of data? Can you somehow intelligently use the same compute to compensate for that lack of data? And I think those are the questions that we and the field will need to grapple with to continue our progress.
Yeah. No, and I think this point about data, the other thing I wanted to touch on, because this is something obviously at scale that we focus on, and I think that the large language models, thankfully, because you can leverage the internet, really, like all the fact that like all this data has existed and been accumulating for a while, you can show some pretty incredible things. In all new domains, you need efficient ways to generate lots of data, right? And I think that there's this whole question was like, how do you make it so that each ounce of human effort that goes into generating some data produces as much data as possible? And I think that like something that we're passionate about, that I think we've talked a little bit about, is like, how do you get like a Moore's law for data, right? How do you get more and more efficiency out of like a human effort in producing data? And that might require novel new paradigms, but is something that I think is required for, in this lawyer for example that you mentioned. Like, we have a pretty finite set of lawyers. How do we get those lawyers to produce enough data so you can create some great legal AI?
The choices that we have is either improve our methods so that we can do more with the same data, or do the same with less data. And the second is, like you say, somehow increase the efficiency of the teachers.
Yep.
And I think both will be needed to make the most progress.
Yeah. Well, it's kind of like, I really think Moore's law is instructive, right? Like, to get these chips performing better, people try all sorts of random crap. And then the end output is that you have chips that have more transistors, right? And I think this, like, if we think about it as like, do we have models that perform better with like certain amounts of data or certain amounts of teaching? How do we make that go up?
Yeah, I mean, I'm sure that there will be ways to do that. I mean, for example, if you ask the human teachers to help you only in the hardest cases, I think that will allow you to move faster.
I want to switch gears to one of the offshoots of the large language model efforts, which is particularly exciting, especially to me as an engineer, probably most people who spend a lot of time coding, which is Codex, which demonstrated some pretty incredible capabilities of going from sort of natural language and to code, and sort of being able to interact with a program in a very novel new way. I'm kind of curious for you, what excites you about this effort? What do you think are the reasonable expectations for what Codex and Codex-like systems will enable in the next few years? What about far beyond that? And ultimately, why are you guys so excited about it?
For some context, Codex is pretty much a large GPT neural network that's trained on code. Instead of training to predict the next word in text, it's trained to predict the next word in code. The next, I guess, token in code. And the thing that's cool about it is that it works at all. Like, I don't think it's self-evident to most people that it would be possible to train a neural net in such a way so that if you just give it some representation of text that describes what you want, and then the neural network will just process this text and produce code, and this code will be correct, and it will run. And that's exciting for a variety of reasons. So first of all, it is useful, it is new. It shows that, I'd say, code has been a domain that hasn't really been touched by AI too much, even though it's obviously very important. And it touches on aspects where AI has been, today's AI, deep learning, has been perceived as weak, which is reasoning and carefully laying out plans and not being fuzzy. And so it turns out that, in fact, they can do quite a good job here. And like one analogy, one distinction between codex and language models is that the codex models, the code models, they allow you to, in effect, they can control the computer. It's like they have the computer as an actuator. And so that makes them much more, it greatly it makes them much more useful. You can do so many more things with them. And of course, we want to make them better still. I think they can improve in lots of different ways. Those are just the preliminary code models. I expect them to be quite useful to programmers, and especially in areas where you need to know random APIs, because these neural networks, so one thing that I think is a small digression, the GPT neural networks, they don't learn quite like people. A person will often have somewhat narrow knowledge in great depth, while these neural networks, they want to know everything that exists, and they really try to do that. So their knowledge is encyclopedic. It's not as deep. It's pretty deep, but not as deep as a person. And so because of that, these neural networks, in the way they work today, they complement people with their breadth. So you might say, I want to do something with a library I don't really know. It could be some existing library, or maybe the neural network had read all, the code of all my colleagues, and it knows what they've written. And so I want to use some library I don't know how to use. The network will have a pretty good guess of how to use it. You'd still need to make sure that what it said is correct, because such is its level of performance today. You cannot trust it blindly, especially if the code is important. For some domains where it's easy to undo anything that it writes, any code that it writes, then I think you can trust it just fine. But if you actually want to have real code, you want to check it. But I expect that in the future, those models will continue to improve. I expect that the code neural networks will keep getting better. And I think the nature of the programming profession will change in response to these models. I think that in a sense, it's a natural continuation of how in the software engineering world, we've been using higher and higher level programming languages. At first, people wrote assembly, then they had Fortran, then they had C, now we have Python, now we have all these amazing Python libraries, and that's a layer on top of that. And now we can be a little bit more imprecise, we can be a little bit more ambitious, and the neural network will do a lot of the work for us. And I do think that, I expect something similar to happen across the board in lots of other white-collar professions as well. If you think about the economic impact of AI, there's been an inversion. I think there's been a lot of thinking that maybe simple robotics tasks will be the first ones to be hit by automation. But instead, we are finding that the creative tasks, counterintuitively, they seem to be affected quite a bit. If you look at the generative neural networks, in the way you generate images now you can find it on Twitter, all kinds of stunning images being generated. Generating cool text, that's happening as well, but the images are getting most of the attention. And then with things like code, things like a lot of writing tasks, this is the white-collar tasks, they are also being affected by these AIs. And I do expect that society will change. As progress continues to make, society will change. And I think that it is important for economists and people who think about these questions to pay careful attention to these trends, so that as technology continues to improve, there are good ideas in place to like in effect, to be ready for this technology.
Yeah, there's a number of like really, again, interesting nuggets in there. I think one is that I think like one of the big ideas behind codex or codex-like models, right, is that you go from being able to go from human language to machine language, right? And you kind of mentioned like, oh, all of a sudden the machine is an actuator. And if you think about like, I think many of us, when we think about AI, we think about like the Star Trek computer. You know, you can just ask a computer and it'll do things. You know, this is a key enabling step, right? Because if all of a sudden you can go from how we speak, how humans speak, to things that a machine can understand, then you like bridge this like key translation step. So I think that's super interesting. You know, another thing that this inversion that you just mentioned about is super interesting, because I think that, you know, one of the things that my beliefs on this is like, hey, this is the reason that some things have become much easier than others. You know, it's all a product of availability of data, right? There are some areas where there just exists lots and lots of digital data that you can kind of suck up into the algorithms, and it can do quite well. And then in things like robotic tasks or setting a table, or you know, all these things that we've had a lot of trouble building machines to do, you're like fundamentally limited by the amount of data you have. First, just by the amount of data that's been collected so far, but also like, you know, you can only have so much stuff happening in the real world to collect that data. I'm curious, how do you think about that? Or do you think it's actually something intrinsic to the sort of like creative tasks that is somehow more suited to current neural networks?
I think it's both. I think it is unquestionably true that so we can take a step backwards. At the base of all AI progress that has happened, at least in all of deep learning and arguably more, is the ability of neural networks to generalize. Now, generalization is a technical term, which means that you understand something correctly or take the right action in a situation that's unlike any situations that you've seen in the past in your experience. And you can see, and so now a system generalizes better if from the same data, it can do the right thing or understand the right situation in a broader set of situations. And so to make an analogy, suppose you have a student at a university studying for an exam. That student might say, this is a very important exam for me. Let me memorize this. Let me make sure I can solve every single exercise in the textbook. You know, such a student will be very well prepared and could achieve a very, very high grade in the exam. Now consider a different student who might say, you know what, I don't need to know how to solve all the exercises in the textbooks, as long as I got the fundamentals right. I read the first 20 pages and I feel I got the fundamentals. If that second student also achieves a high grade in the exam, that second student did something harder than the first student. That second student exhibited a greater degree of generalization. They were able to, even though the questions were the same, the situation was less familiar for the second student than the first student. And so our neural networks are a lot like the first students. They have an incredible ability to generalize for a computer, but we could do more. And because their generalization is not yet perfect, definitely not yet at a human level, we need to compensate for it by training on very large amounts of data. That's where the data comes in. The better you generalize, the less data you need, / the further you can go with the same data. So maybe once we figure out how to make our neural networks generalize a lot better, then all those small domains, we don't have a lot of data, it actually won't matter. The neural network will say, it's okay. I know what to do well enough, even with this limited amount of data. But today, we need a lot of data. But now, when it comes to the creative applications in particular, there is some way in which they are especially well suited for neural networks. And that's because generative models play a very central role in machine learning. And the nature of the generations of generative models are somehow analogous to the artistic process. It's not perfect. It doesn't capture everything. And there is certain kinds of art which our models cannot do yet. But I think this second connection, the generative aspect of art and the ability of generative models to generate new plausible data is another reason why we've seen so much progress in generative art.